Recall that yesterday we not only parameterized the circle, but we described this semicircle in 3 different ways. And we wanted to use each of those 3 different ways to find the equation of a line tangent to the semicircle at a given point. The given point was, did I put it at 120 degrees? That looks right in my memory. In each of those 3 different ways, we wanted to find dy dx, the slope of the line tangent to the semicircle. And in each of the 3 different ways, we use different methods to do it. For the first one, where we described the semicircle with a function, we were just able to take the derivative. We had a function of one variable. We took the derivative with respect to that variable, dy dx. In the second version, where we had an equation with the x squared and the y squared, that was not a function. X squared plus y squared equals 9. We used implicit differentiation. And the dy dx showed up when I took the derivative of y squared with respect to x. I got 2y times dy dx. That's how we got at the derivative of y with respect to x. So in the third one, we have a parameterized parametric equations for this semicircle. X is 3 cosine t, y is 3 sine t. T goes from 0 to pi. We didn't need a direction, but we got one, so there it is. The problem we ran into is that when we take derivatives, we have dx dt and dy dt. Now, we might try to do the implicit differentiation thing, but that would give us dt dx, and we don't have any information on that. We don't know how that's going to get us to dy dx. But we have dy dt and dx dt. But we need dy dx. The slope is dy dx. But we have derivatives with respect to t. Any ideas what we can do?
You can find you can find dy.
Not quite the inverse of dx dt, a specific inverse. The multiplicative inverse. We can divide by dx dt. What we want is dy over dx. So if I take dy over dt and start treating these like differentials, take dy dt and divide it by d. I spelled t wrong. This time it didn't fall over. I actually spelled it wrong. I'll take the dy dt and divide by dx dt, and then the dt parts will cancel out. We'll treat them like differentials and cancel out the over dt part. Oh, I wrote this the other way. I didn't do that. So dy dt is 3 cosine t, and dx dt is -3 sine t. If you'll notice what we have here, we got 3 cosine t over -3 sine t. Notice that 3 cosine t is the x and 3 sine t is the y. So when we put this together, it was dy dt over dx dt. But if we think back to the derivatives that we had before, which I conveniently didn't erase, the dy dx using implicit differentiation ended up being -x over y. And so here's the minus, 3 cosine t is x, 3 sine t is the y. So this is the same derivative that we had before, it's just the parameterized version of it. So one of the things that we want to notice, one of the things that we could do is just make that substitution and then just use the point as we have it. Well, let's pretend that we don't notice that. What we have to do then is to figure out what value of t will land us at -3/2 and 3√3 over 2. That is, what is the value of t that will land us at that point? And that's why I chose -1/2 and √3 over 2. Because what I want is I want 3 cosine of t to be negative 3/2. If we divide out the 3's, that tells us that cosine of t is negative 1/2. And that tells us that t is going to be a 60-degree reference angle in quadrant 2 or quadrant 3. Oh, 60 degrees. We should do this in radians. Pi over 3 radians based on the location of the point, we can clearly see that we want this to be in quadrant 2. So we want pi over 3 in quadrant 2. And so this one is going to be pi over 3 in quadrant 2 will be 2 pi over 3. We notice that because we know that we want quadrant 2 because that's where the point is. This point is in Q2. If we come at this from the other direction, if we look at the y is 3 sine t. And we want that to be 3√3/2, which means we want the sine of t to be the square root of 3/2. Since the sine of t is to be a positive value, that means we're in quadrant 1 or quadrant 2. And it's still 60 degrees. So t is pi over 3 in quadrant 1 or quadrant 2. We happen to already know that this point is the one in quadrant 2. And so that's going to be 2 pi over 3. But if we didn't have, well, we would have the point. We had to have the points. If we didn't, we would look for, we want a pi over 3 reference angle in quadrant 2 or 3, or pi over 3 reference angle in quadrant 1 or 2. The one that matches is quadrant 2. We knew that going in. We had to know that going in because we were given the points. Because we had to know the points based on just to get these equations. But now we want the slope at this point, so we'll take the slope and evaluate it at 2 pi over 3. So the slope is going to be dy dx evaluated at 2 pi over 3. So that's going to be 3 times the cosine of 2 pi over 3 over negative 3 sine of 2 pi over 3. Three cosine of 2 pi over 3 is negative 3/2, because of course it is, because the numerator is x. Because I needed a pi over 3 reference angle in quadrant 2. So 3 cosine of 2 pi over 3 will be negative 3/2. And negative 3 sine of 2 pi over 3 will be negative 3, sine is positive. The negatives cancel. The negatives cancel. The over 2's cancel. The 3's cancel. And we're left with the same thing that we had before, 1 over √3. all three calculations led us to the same equation because of course it did. If it didn't, then something would be seriously wrong with one of our methods. We want to point out the correlations. One of the correlations that we didn't point out yesterday, since we just pointed out that we ended up with 3 cosine t over 3 sine t, which was x over y. That was the same as the expression we had yesterday, negative x over y. Also, remember that we also solved for y. We saw y equals the positive square root of 9 minus x squared. If I plug that into my expression up here, I get negative x over the square root of 9 minus x squared. And this is the derivative that we had as a function of x yesterday. That was the same derivative that we had yesterday. Because they're all the same derivative. It was all dy dx. We were just looking at dy dx in different form. We have 3 different descriptions of our semicircle that led to 3 different forms of our dy dx. So it makes sense that they're all just direct replacements of each other in different languages. It's the same thing in different languages. Question? Like yes. Yeah. See. Or no. 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 I should make that middle one 9. 9. Any questions?
The point is that
Yeah, everybody, like almost everybody uses no. Which made me wonder if some aliens showed up and we told them no, would they know what we're talking about? Like with no hand gestures or anything like that. No, like, no. Questions? Comments? Easy one or messy one? Easy one. Oh, not 2 though. Let's not use 2. Yeah, that'll be good. So here's our next problem. I want to connect the points 0, 0, and 3, 9. 0, 0. In 2 different ways with 2 different paths. One, just a line. the second one with a parabola. Actually, I want to specify specifically with this parabola. That way I'll give you 3 pieces of information. My original plan, since this is a problem that I'm not going to be finishing today, my original plan was just to give you those 2 pieces of information and see if you could just work with those 2 pieces of information. There's a parabola that connects 0, 0, and 3, 9. But then I decided to lock it down to exactly one parabola by specifying 0, 0 is the vertex. So I gave you 3 pieces of information. Why did I need 3 pieces of information? Just to make sure we're describing the same parabola. How many parameters do we have in a parabola? We must have 3 because I just said we need 3 pieces of information, right? If I want to describe a line, the equation is y equals mx plus b. There's 2 parameters, where it starts and what direction it goes. So we need 2 pieces of information, like 2 points. But if I want to describe a parabola, parabolas have more parameters. Because parabolas are quadratic, so I have ax squared plus bx plus c. That means I need to tell you 3 things to lock down one parabola. Or in vertex form, a times the square of the difference of x and h plus k. The sum of the product of a and the square of the difference of x and h. I think I said it right finally. But there's 3 things, a, b, and c, or a, h, and k. So I needed to give you 3 pieces of information to get one parabola. Here I've given you 3 pieces of information. Actually, I just told you which parabola I wanted to use. My prediction was going to be that everybody is going to pick y equals x squared anyway. But that is assuming that 0, 0 is the vertex. So I'm just going to give you 3 pieces of information. 0.00, 0.39, and 0, 0 is the vertex. Is there another parabola that contains 0, 0, and 3, 9? So that's another variation of this question. If so, how many? That's all beside the point. We have currently locked it down to a parabola, specifically this parabola. We have a line connecting 0, 0, and 3, 9. There's only going to be one of those, but part B is not a parabola, it's the parabola. Y equals x squared. The first one you would have thought of anyway. Here's what I want to know. What is the length of the path from each path from 0, 0 to 3, 9? What is the distance from 0, 0 to 3, 9 along each path? That's what I want to know. Which one is shorter, by the way? Are they the same? It's the two endpoints. No, they're not going to be the same. Which one is shorter? The straight line. The shortest distance between 2 points on a plane is a straight line. So there's that. So it's going to be longer from 0, 0 to 3, 9. I want to know, what is the distance from 0, 0 to 3, 9 along each. Any questions on what the question is? Here's what I do very often in this class. I pose a problem, and then I just wait around for you to answer while you're sitting in the classroom. This is a terrible situation for trying to answer a problem. This is like when I go to a meeting. I don't know why it took me 20 years to realize this. This is why when I go to a meeting and they say, here's what we need to accomplish today, and it's like a group project, I'm like, well, that is not how I operate. I cannot come up with ideas if everybody's standing around waiting for me to come up with ideas. You know what I mean? I can't like sit around and say, oh, this is the time when we're going to work on this problem. It's like, oh, I need time to think about the problem on my own before I can talk to other people. Which is why Zoom meetings are great, because I can just turn off my camera and put up a loop of me looking like I'm thinking. Right? It's a defensive thinking phase, right? Like if I'm all, what is the derivative of this function? And I start scanning the room. I switch to Terminator view. And it's like, oh, you want to put up the defensive face. We're like, It's like, hold on, I'm still thinking about it. And it doesn't matter what I ask, right? Because I'll be like, oh, what's 5 plus 7? And people are like, oh, no, I didn't even hear the question. I'm thinking about it. That's a tough one. Like, oh, dude, it's 5 plus 7. It's like something like 10 plus something else. I don't know. That's why I'm asking. But then some teachers like start scanning the room. Now in here, you don't worry about it so much, because how many times have I looked through the room and picked someone and called on them by name? Yeah. How many times have that happened? Never, because I don't do that. You could tell right away if a teacher never calls on students by name, that's because they were the student that didn't want to get called on. Some of you are like this. Some of you wouldn't care if I called on you by name. Do you know what I mean? Yeah. So I'd be like, oh, all right, Bob, what's the answer to this question? And I'd be like, oh, well, let me tell you, because they're okay with being called on by name. But there are some students who are like, oh, Fred, what's the answer? The next day, Fred's like, I don't know. And the next day, Fred would just stop coming to class. Because he's going to be like, well, if you're going to fucking call on me, I'm not going to be here anymore. So that's your spectrum. All right, that's your spectrum of students. Like at one end, if you call on them, they will leave. On the other end, students that will wait and just volunteer information. That's their spectrum. And you can tell based on what the teacher does in class, what kind of student they were. I've never called on any of you individually by name. And so you can tell that I wouldn't drop the class, but I would definitely sit in the back. And I would put on my defensive I'm thinking face. So the teacher's like, oh, well, what should we do next? Hang on, I'm still thinking about it. And then if you still called on me, then I'll drop the class. But subtly drop the class. Like I go in and like I'd be like absent for a couple of days. And then I would file my paperwork and drop the class. I wouldn't make a big show of it, right? I wouldn't like stand up and walk out flipping everybody off. You know what I mean? So anyway, this is what I want you to think about. And this is what we're going to figure out tomorrow. So take some time, figure out how to find the distance from 0, 0 to 3, 9. Okay, the first one you have to know. If you're like, oh, I'm not sure how to find the distance. It's like the distance, and there's a formula for it. It might be called the distance formula, if I remember correctly. So that one you should know already. But this one is more complicated. How can we figure out the distance from 0, 0 to 3, 9 along a parabola? How far is it along the parabola? Because I didn't give you something for which we have a perimeter formula. If I'm like, oh, here's a circle, you're like, oh, I just use a piece of a circle. Here's a rectangle, I'll just use a rectangle. Because I have those perimeter formulas. We don't have the parabola perimeter formula. We're going to have to make some shit up. Any questions? No, because I have a starting point and an ending point. If I said, what's the length of this parabola, that would be infinite, because it goes on forever and goes forever. So yes, like just like a line. But I don't have a line, a full parabola. I have a parabola, a parabolic segment of this finite piece. We know it's going to be longer than this distance. We know it's going to be shorter than the L from 0, 0 to 3, 0, and then from 3, 0 to 3, 9, if I add those two up. So we've got a minimum distance, and we've got a maximum distance. Because if we just bend it all the way down to this backwards L shape. So we know that if we get something more than 12 in our calculations, nah, that's not right. Because this is definitely going to be shorter than going horizontally and vertically. Any questions about what we have to do? Keep in mind, this is calculus class, and this is changing continuously. So it's going to be a combination, possibly. But yeah, differentiation does definitely enter it. Think about how differentiation could enter into this problem. Think about what we're doing. We're trying to do something. We're trying to find the distance between these 2 points. But it's all bent, right? We have a formula for the distance between 2 points, but this is all bent. So we've got to think of the calculus way and how it applies to it. All right, that's going to do it for today. This is our problem that we're going to be working on tomorrow. You've got a lead time to think about it. Tomorrow, we'll try to sort this out. That's it for today. I'll see y'all on tomorrow. Everybody have a good day. Thanks for playing.